Hey everybody, and welcome to our first video in Unit 6, which will be all about electron dot notation and the different types of bonds. This might be a long video, but I'd rather get it all done in one shot rather than make this into a bunch of very short videos on different topics. Anyway, before we get started on the types of bonds, I want us to focus on electron dot notation. So, we've talked about valence electrons already. We've looked at the electron configuration for things. We're going to use that information now to help us with bonding. So what is the electron dot notation? An electron dot notation is like another type of electron configuration notation. In this case, though, we will only use the valence electrons, and we're going to represent those around the symbol of an atom. So it's an electron configuration notation in which only the valence electron of an atom are shown, which are indicated by dots that are placed around that element's symbol. So for example, if we have the element fluorine, fluorine has 7 valence electrons. If you remember back, I think it was Unit 3, we talked about that. So fluorine's in the 7th group on the periodic table without the transition metals. So it has 7 valence electrons. We can represent that by drawing dots around the symbol for fluorine. So we don't have to draw this part, but I always like to imagine that there's just a box around that because that's going to tell us kind of where to put the dots. And it doesn't matter where you start placing these dots, you just pick one side of the box. It doesn't matter. I happen to choose this side. So we have 7 dots that we're going to place around to represent our electron dot notation. However, just like Hund's rule where we unpair electrons before we pair them, we want to unpair our dots around the circle or around the square once before we go and pair them up. So if I look at fluorine here, I have 1 dot, 2 dots, 3 dots, 4 dots. I went all the way around each side of the box once, and then I'm going to double them up. So I'll do 5, 6, and 7. So this is the electron dot notation for fluorine. And like I said, it doesn't matter where you start as long as it has those 7 dots around it, 3 of which are in pairs. So this is a pair, this is a pair, and this is a pair, and then I have 1 single electron that's left unpaired. This is a pretty easy concept, so let's just jump right into sample problem 1 and do those examples. Okay, so let's start off with electron dot notations. So I don't have a periodic table here, so you'll just have to remember, of course, because I already taught how to determine how many valence electrons something has. I'll quickly go over it here. But hydrogen is in the first group on the periodic table, so this has 1 valence electron. So what we'll do is we'll draw hydrogen's symbol, and I can place that 1 valence electron on any side. I want to place it there for the sake of this problem. That's where I'm going to put it. You could put that on any side of the hydrogen, and that's correct. Let's try nitrogen. So nitrogen has 5 valence electrons. So I'll write 5 valence electrons. And that's because nitrogen is in group 15 on the periodic table. So without counting those transition metals, it's got 5 valence electrons. I could start putting electrons on any side of this that I want to. So I'm going to pick here for this one. And remember, I'm going to go around all 4 sides of this once, like Hund's rule. Okay, we want to unpair those electrons once, and then we can go back and pair them. So at this rate, this is correct for the electron dot notation for nitrogen. And remember, it doesn't matter which side has the lone pair on it, as long as it has 1 pair of electrons. Phosphorus is actually right below nitrogen, so it also has 5 valence electrons. Let's pick a different side. I'm going to start here for this one. So I'll do 1, 2, 3, 4. Go around there once. Let's go back this way. Why not? We'll put my lone pair of electrons on that side. So remember, as long as we have 3 unpaired electrons and 1 pair, we're good to go. Neon is a noble gas, has 8 valence electrons. So neon's symbol is Ne. Let's go ahead. I'm going to start on the top here. 1, 2, 3, 4. I can go all the way around once. And then I will start to double up. So I'll do around a second time. So notice that neon has, it's maxed out with its electrons. It has 8 valence electrons around it. That's why neon is very stable. Carbon is right before nitrogen, so carbon has 4 valence electrons. Draw carbon symbol, and again, we're just going to place the electrons, one on each side. There we go. Carbon wants 4 more electrons, actually, which we'll get into the next section, but it should have 4 electrons that are not in pairs. They're singled up. Magnesium, alkaline earth metal, 2 valence electrons. It doesn't matter where you place them. I'm going to draw them on 2 different sides because why not? There it is. You could draw, one on top and bottom. You could draw them right next to each other. What is not correct is this. Remember, we have to go around once before we start to pair them up. So that is incorrect. Potassium, alkali metal, 1 valence electron. I'll throw it over there. Boron has 3 valence electrons. So draw boron symbol. 1, 2, 3. Just like that. Nice and easy. Pretty simple, right? But chemists don't just sit around and doing this all day. We have to take this information and we draw more complex structures with them, which is what we're going to do next. Now this brings us to the octet rule. So atoms want to bond so that way they have all of the electrons that they want to be stable. Like we said, that's why the noble gases are stable. They, except for helium, have 8 valence electrons. They satisfy the octet rule. That's why they don't react with anything. So what is the octet rule? The octet rule states that atoms want to either gain, lose, or share electrons in order to have 8 electrons in their outermost energy shell. And depending on the electronegativity or ionization energy, things we've also talked about in the past, everything kind of culminates in this unit, which is fun. Depending on those values, we can determine, is it going to gain or lose an electron? Would it rather share an electron? But anyway, atoms want to have 8 electrons in their outermost shell. So we could see just by this image here, we have neon doesn't want any because neon already has 8 valence electrons in its outermost shell. These metals like to give their electrons away, whereas your nonmetals tend to gain electrons because they have very high electronegativities. Which brings us to chemical bonding. So atoms will try to satisfy that octet rule by partaking in some sort of chemical bond. And there are 3 types of chemical bonds that we can talk about. But first, let's get this down here. So a chemical bond is an attraction between atoms that allows the formation of chemical substances that contain 2 or more atoms, right? So it's a way that 2 different atoms or 2 different elements will combine with one another to form something new, to get something more complex. We don't have a lot of pure substance elements around. A lot of things are going to come in compounds, and they have to bond to one another in order to create those compounds. And there's 3 different types of bonds that we can form. We could form either ionic bonds, we could form covalent bonds, or we can form metallic bonds. And again, the type of bond is going to depend on what type of elements are partaking in that particular bond. We're going to focus on ionic bonds first. So, an ionic bond, there's a lot of definitions right now, I apologize. An ionic bond is the complete transfer of valence electrons from a metal to a nonmetal that produces 2 oppositely charged ions. So an ionic bond is a transfer of valence electrons. We have one element is going to steal electrons from another element. The electrons are totally taken away. in this case. And when that happens, when something gains something negative, the one that stole the electron is going to therefore have a negative charge, whereas the element that gave its electron away, if you lose a negative thing, it becomes positive. So you produce two oppositely charged ions, an ion being a charged particle, which I think we're going to get down here in a second. So here's a nice little simulation thing that's being shown here. So sodium, in this case, has one valence electron. This is going to keep doing it, so I'm just going to talk over it. But sodium has one valence electron in its outermost shell, okay? Elements strive to have 8 valence electrons in their outermost shell. When sodium loses this one, we still have the 8 valence electrons in the shell below. So sodium is stable when it loses that one valence electron. Fluorine, on the other hand, has 7 valence electrons. It wants one electron really, really badly. So fluorine, because it's so electronegative, is going to steal an electron from sodium, which is what it's representing down here. That one valence electron from sodium in this third shell is getting transferred to fluorine in its second shell. So therefore, fluorine has 8 electrons in its outermost shell, and sodium also now has 8 electrons in its outermost shell. When that happens, when sodium loses a negative thing, it becomes positive. When fluorine gains that negative thing, it becomes negative. We have to remember that electrons are negative, so even though it's gaining something, it's becoming positive. That attraction between positive and negative is the ionic bond. So we'll see here, once this transfer happens, right, these two things are going to attract one another. That's an ionic bond. So the nonmetal, again, in this case, so just like that last picture, we saw sodium. Sodium is a metal. Fluorine was a nonmetal. Nonmetals tend to have very high electronegativities, like fluorine we've talked about. Fluorine, chlorine, bromine, oxygen, nitrogen, very electronegative elements. Those nonmetals have the ability to steal an electron from a metal because those metals do not have high electronegativities. So in this case, the nonmetal will steal the electron from the metal because the nonmetal has a very high electronegativity. Now you might not remember what electronegativity is, so let's go ahead and talk about those quickly. Electronegativity, again, sorry, lots of definitions. Electronegativity is the tendency of an atom to attract electrons to itself. Something that's super electronegative wants electrons really badly. So there's a nice little silly little clip art there to kind of represent that. Most electronegative element on the periodic table is fluorine. Chlorine is also very electronegative, as is oxygen. So those really tiny elements towards the top that don't have full outer shells. We also have an ion, which I've mentioned before. Ion is any group or group of atoms that has a charge. So here's a whole bunch of different ions that are shown up here on the screen. And you'll see I color-coded them. There's a reason for that. So any type of ion that is a positively charged ion is what we call a cation, So a cation is a positively charged ion. So we'll see this potassium right here is positively charged. Aluminum, positively charged. Magnesium, this is the ammonium ion, positively charged. Not only are they ions, more specifically, they are cations. And I always remember the difference because the word cation has a T in it, and a T kind of looks like a plus sign. So cations are positively charged ions, whereas anions are your negatively charged ions. So that's your NO3, your nitrate group, your phosphate group, your chloride, and your oxide right here are all called anions. So they're all ions, but we can further break them down into cations, positively charged, and anions, which are negatively charged. So let's take a look here. So let's show that formation of that ionic bond between sodium and chlorine. So here's sodium with its one valence electron. Sodium is a metal. We also have chlorine with its 7 valence electrons, which is a nonmetal. And ionic bonds tend to happen between metals and nonmetals. So what's going to happen is that very electronegative nonmetal, that chlorine, is going to steal the electron from sodium, just like that, because now chlorine has 8 valence electrons in its outermost shell, and so does sodium. So sodium, even though there's no electrons here, we have to remember that the shell beneath it is totally filled. When that chlorine steals that electron, chlorine becomes negative. It's gaining a negative thing. Its charge is -1. Sodium has lost a negative thing, so it becomes positive. Because this transfer of 1 electrons satisfies the octet rule for both of these elements, this is a happy ionic bond. So the ratio of these two elements bonding is a 1-to-1 ratio. 1 sodium atom gives its 1 electron to 1 chlorine atom. And we say that that is 1 formula unit. We're not always going to have a 1-to-1 ratio. We'll see the next one where that's not the case. But we do have 1 singular formula unit. 1 sodium switches electrons with 1 chlorine. And a formula unit is the lowest whole number ratio of ions that are represented in an ionic compound. So, like I said, in this case, it is in fact a 1-to-1 ratio. Let's try the next one where it might not be 1-to-1. So I have the formation of an ionic bond between calcium and fluorine. So it'll give it away here, right? I got 2 fluorines that are listed. Calcium is your metal, 2 valence electrons. And in this case, I have 2 fluorines, each with 7 valence electrons. So we see those 7 electrons represented there in different colors. To form this ionic bond, so I'm just going to put these here again. This first fluorine with the light orange can attract 1 of the electrons from calcium. Now this fluorine is happy. It satisfies the octet rule. It has all 8 valence electrons around it. However, calcium still has 1 and it wants to get rid of that 1. So what's going to happen? Well, that second fluorine is going to attract that electron and steal it away from calcium. What does that mean? Well, calcium now has a full outer shell beneath it, so it's satisfied, and so do each of these fluorines are all satisfied with their octet rule. When calcium has lost 2 negative things, it has a charge of +2. So calcium's charge is +2 because it lost 2 negative things, whereas each fluorine gained 1 electron. So each fluorine now has a charge of -1. Notice that the sum of all of these charges is 0. So I have a +2, a -1, and a -1. The sum of all of those is 0, which is what we want. And the final formula unit is CaF2. 1 calcium atom will trade electrons with 2 fluorine atoms to produce 1 formula unit of CaF2. The ratio is 1 calcium atom to 2 fluorine atoms, CaF2. We're going to learn in the next unit, we tend to write the metals first in the formula. So normally it's metals Ca, and then we write the nonmetal after that, F2. CaF2, NaCl. You're going to see the metals always listed first. Let's try sample problem 2 together in the notes. Okay, so let's do sample problem 2. Draw the formation of an ionic bond between potassium and sulfur. We're going to do some different colors here. So potassium is an alkali metal with 1 valence electron. So I'm going to draw potassium with its 1. Oh, what in the world was that? Let's get rid of that thing. That was weird. And potassium is a metal, of course, so let's label that. It's got a metal right there. Let's do sulfur in a different color. Let's do purple. So I'm going to do a plus sign here, and I'll do sulfur next door. Sulfur has 6 valence electrons. So I'm going to do 1, 2, 3, 4. You got to go around once, and then I'll do 5, 6. I'll place them like that. And sulfur, of course, is a nonmetal. Nonmetal. Now, just by judging from this sulfur, in order to satisfy that octet rule, it has 6 valence electrons around it now. It does need 2 more. So this 1 electron from potassium can get transferred over here. Now, the only thing is that sulfur still needs 1 more electron. So guess what? Where is it going to get that last electron from? Well, another potassium atom is needed. So let's draw that second potassium. I'll do this one here, plus another potassium, which is a metal. I'll label that down below. And we'll show that transfer of electrons. So this second electron, we're going to go all the way around here. It could go right over there. So what does that mean? Well, if I draw the products of this, I have 2 potassiums. So I have a potassium. This now has no electrons around it. I have a sulfur with 8 electrons around it. So let's see. I have a sulfur, and I have 1, 2, 3, 4, 5, 6. Its original 6, but it also took electrons from each potassium. So here's 1 from this potassium, here's 1 from the second potassium, and I have a potassium there as well. Now, what does that mean? Well, each potassium lost a negative thing. If it lost a negative thing, its charges will be +1. Each one has a charge of +1. Sulfur, on the other hand, gained 2 negative things. So since sulfur gained 2 negative things, its charge is now -2. Notice how the sum, +1 minus 2 plus 1 gives me a sum of 0. That's what we want. We want to make sure that the sum of all of those charges is 0. And the formula unit is going to be K2S. 2 potassium atoms trade or give their electrons to 1 sulfur atom. Now, I don't expect you to get this correct all of the time now, but just a little foreshadowing here. We normally do the metal first in the formula, and then we put the nonmetal after that. So you'll always see the metal first. Formula unit is K2S. So those were all ionic bonds where we're dealing with a metal and a nonmetal, where we have a transfer of electrons. Not the case for everything. So there's a second type of bond, which is a covalent bond. And a covalent bond results from the sharing of electrons between 2 nonmetal atoms. So notice how in this case we have 2 nonmetals. So this would be, like in this case on the screen, oxygen bonded to itself. Both oxygens are nonmetals. They're going to share their electrons between them, so they have 8 valence electrons in their outermost shell. So with this oxygen here on the left, it looks like in its outer shell it has 1, 2, 3, 4, 5, 6. And this oxygen on the right also has 6 electrons in its outermost shell. Each oxygen wants to get to 8 in order to be stable. So what they'll do is they'll share 4 electrons between them. So this oxygen will share 2 electrons from it, and this electrons will share 2 electrons from it. So that way, since they're sharing those electrons, they both have 8 in their outermost shell. So we're not stealing away, we're not making any charged particles, they're simply sharing between the 2. There are, however, 2 types of covalent bonds. So we have to think of bonding as a spectrum. Okay, so we have something that could be totally covalent. They share their electrons totally evenly, like the perfect children. And then you have ionic, where you have 2 children that are always stealing their toys from one another. Hopefully we have some sharing somewhere in the middle. So there is a spectrum, okay? A perfectly nonpolar covalent bond means that you have 2 atoms that share their electrons totally equally. Equal distribution of charge, there's no fighting between electrons. A great example would be bromine bonded to itself. Neither bromine wants electrons more than the other one because they have equal electronegativities. So as a result, they are sharing those electrons the same amount, okay? Totally equal distribution. It's not the case for everything. Sometimes you can have an unequal distribution of charge. That's what we call a polar covalent bond. A great example of that would be if hydrogen bonds to bromine. So bromine is in your halogen group. It's pretty electronegative. Hydrogen, not so much. So even though they're both nonmetals, bromine is just a little bit stronger that it's going to pull electrons towards itself. So as a result, more of your electrons are going to live around this bromine. They're still being shared, but they're not being shared the same amount. One kind of is making electrons come towards itself a little bit more. So what we say for that is that this bromine has a partial negative charge. This little symbol here is a Greek letter delta. It's a lowercase d. And that delta negative means that most of the electrons are going to live around bromine, and you're not going to have as many electrons around hydrogen. So this will have a partially positive charge. More of the electrons, higher electronegativity gets the partial negative. So two nonmetals share their electrons because they have similar electronegativity values. They're similar. They might not be the same, like in a nonpolar covalent bond, but they're still pretty close, so they could still share. Now, what if they have electronegativities that are very different, opposite sides of the periodic table? Well, that's when I have an ionic bond. One atom steals the electron from the other. The nonmetal steals the electron from the metal. So what chemists can do is they can quantitatively determine if a bond is ionic, nonpolar covalent, or polar covalent by looking at the electronegativity values. And we can subtract these values from one another. It doesn't matter which way you subtract it as long as you get a positive value. The difference between those two values, so after you subtract them, you get a value, a number. That number is going to give us a general idea about the type of bond that exists between both of those atoms. It does say, however, it gives us a general idea, but because it's important to remember that a bond is just one or just another. They could have properties of both. So here's a value of electronegativities, which you will be given. You do not have to memorize this. We'll see that your most electronegative elements are going to be up here in red, and we tend to get less electronegative as we progress over and down to the opposite side. So we can, let's say I want to know what's the type of bond that exists between oxygen and fluorine. Okay, well, fluorine has an electronegativity of 4, and oxygen has an electronegativity of 3.5. So the higher number, 4, minus the lower number, 3.5, gives us a difference of 0.5. That 0.5 then, I can compare that to this little chart right here, which you will also be given. And 0.5 lies within this range, which tells me that the bond that would occur between oxygen and fluorine, had to go back and double check, would be a polar covalent bond, okay? Now you'll see here 0.3 is listed in both of those because remember, this is a spectrum, right? We can't say, oh, that's the cutoff right there. You know, it could be a little bit of this, but a little bit of that as well. So that difference tells us a lot about the type of bond, and it's very simple to do. Take your two elements, subtract them, bigger one minus the smaller one, see where it plugs into that chart. Let's go ahead and do sample problem 3 and get some practice with that. Sample problem 3. So with this one, I'm not going to go back and forth between the electronegativity chart, but you can kind of go back to the page before, page 6 in your notes, and to take a look at these. So I want to know what type of bond exists between chlorine and chlorine. And then it says if it's polar covalent, determine which side of the bond would be partially negative. And if it's ionic, determine the charge on each ion. So I have chlorine bonded to chlorine. I look on the page before. Chlorine's electronegativity is 3.0. 3.0 3.0 minus 3.0, of course, is 0. If I look at that electronegativity difference, that means that the bond that exists between chlorine and chlorine would be a nonpolar covalent bond. These would share their electrons totally equally between one another. Let's try carbon and bromine. So bromine looks like it has a slightly larger electronegativity. Bromine is 2.8, whereas carbon is 2.5. And when I subtract them, I get 0.3. So now we're at the point where, oh, I'm going to D. It's fine, you get the idea. Because this is right on the cusp, it says 0.3 is nonpolar covalent, but it's also polar covalent. Again, this is a spectrum, right? It's not going to be totally clear cut as to which it is. I'm just going to say it's polar covalent. I'm going to go to the one that's above it. We got a little bit of a difference in charge here. Bromine is more electronegative. So because bromine is more electronegative, this side of the molecule will have a partial negative charge. Partial negative. That's what that delta means. It's like kind of unfinished 8 here. It's got a little bit of a negative charge because it wants electrons more. It's pulling electrons more towards itself, whereas carbon is partially positive. It's going to be more positive here because the electrons are being pulled more in that direction. Fluorine and fluorine, nice and easy again. Fluorine's 4.0. I subtract another 4.0, I get 0.0. That's a nice, straightforward, nonpolar covalent bond in between them. Hydrogen and chlorine. Let's take the bigger value. So chlorine is 3.0 and hydrogen is 2.1. So that gives us a difference of 0.9. 0.9 brings us in that polar covalent range. Polar covalent. So the question is, all right, well, which side of this molecule, since it's an unequal sharing, will have the negative charge? Well, chlorine's a lot more electronegative. It's got the value of 3. So if I were to draw just a little bond between them, and I could draw this line to represent that they're sharing, because this chlorine has the higher electronegativity value of 3, I would show the delta negative sign next to chlorine because chlorine's pulling electrons in that direction, whereas hydrogen's going to be missing those, so it would have a partial positive charge. Potassium and oxygen. Ooh, let's see. Oxygen is 3.5. It's electronegativity. It's a bit higher than potassium. Potassium is 0.8. So if I do the difference between them, 3.5 minus 0.8 gives me a difference of 2.7. Pretty large electronegativity difference there. So this is clearly an ionic bond that would occur. I have a complete transfer of electrons. Because I have a complete transfer of electrons, we're not going to have partial negatives here. It's going to be a full-on positive or full-on negative. Who's going to have the positive and the negative? Well, oxygen's got the much higher electronegativity. Oxygen's going to be negative, whereas potassium is going to be positive. We're not going to worry about what the charges are just yet, as long as you know that the more electronegative means it'll have the negative charge to it. Lithium and fluorine. Fluorine is the most electronegative, 4.0. Lithium, not very electronegative, gives us a difference of 3.0. So again, I got a very highly ionic bond there. Fluorine, much higher electronegativity. Fluorine will have that negative charge. Lithium will have that positive charge. Remember, it's full-on negative, full-on positive because it's ionic. Another one, metal and a nonmetal, right? Wow, 3 metals and nonmetals in a row. That's because I'm going out of order. It should have been down that way. Chlorine is 3.0 and sodium is 0.9. So my difference is 2.1. Ionic again, clearly in that section. Chlorine is much more electronegative. It's got that full-on negative, whereas sodium's got that full-on positive. Okay, and that ionic bond is the attraction between positive and negative. Phosphorus and hydrogen, let's see, phosphorus is 2.2, hydrogen's 2.1. Difference of only 0.1, very small electronegativity difference. These electronegativity values are so similar, we say that that's nonpolar covalent. They're really not, you know, phosphorus is not pulling electrons that much more than hydrogen is, nonpolar covalent. We also have fluorine and iodine. So fluorine's got an electronegativity of 4.0, iodine 2.7. Subtract those, we get 1.3. 1.3 is going to bring us in that polar covalent range. So we have a polar covalent bond. So if fluorine has the higher electronegativity value of 4, iodine is 2.7, fluorine's going to have that partial negative charge. It just wants electrons a little bit, whereas iodine would have that partial positive charge. So remember, we're always at a spectrum here with those. So here's the major thing. Ionic bonds are when I have many atoms. They transfer atoms from A to B. The reason why we have many atoms and we tend to form these structures is because when I form those ions, those charged particles, this charged particle can attract lots of negatives that surround it. But overall, the ratio is 1 to 1. Okay, electrons are transferred between atoms from A to B. That's important to know for ionic bonding. And we tend to form these crystalline structures like this, which we'll get into a little bit later in this unit. Covalent bonds, on the other hand, can only occur between 2 atoms, right? Because only 2 atoms can share their electrons. So notice here, the electron pair is shared between atom C and atom D. We'll see here that that electron cloud overlap, that orbital overlap, gives us that sharing of those electrons. So I really like this picture because it's really showing us the transfer and what the structures will look like. Ionic bonds tend to look like this, whereas covalent bonds tend to look like that. Oh, and look, I did circle that for you. So transferred and shared, because that is pretty important. The last type of bond is a metallic bond. So this is pretty easy because, of course, metallic bonds will only occur between metals. It's a strong attraction between closely packed positive metal ions and a sea of delocalized electrons. We tend to call it a sea, the sea of electrons. So what does that mean? I have this image here. In metals, it's only metals where we find a metallic bond. These red spheres are all positively charged metal ions. And all of these metal ions overlap in their electron clouds. So this blue circle shape right here, it's not really a circle. This is one big electron cloud that surrounds all of those metal ions. And these blue dots are electrons. And these electrons are constantly flowing in between those metal ions. So as a result, these electrons are constantly moving. They're delocalized. They don't belong to one particular metal atom. They belong to all of the metal atoms. They're constantly moving. So as a result of these electrons constantly moving, we have properties that give, or the properties of metals are different from those of ionic compounds or covalent compounds. This is why metallic compounds, metals, tend to be very good conductors of heat and electricity, because these electrons are constantly flowing throughout that one big electron cloud. That's why they're malleable. That's why they're ductile. That's why they're lustrous, because light reflects off of those electrons that are constantly moving. And that's it for metallic bonds. I mean, really, if you have a sample of copper, copper is a metallic bond. It's made up of just metals. That's it for this particular video on the types of bonds. Our next video, we're going to dive a little bit deeper into covalent bonds, where we're going to draw some Lewis dot structures and talk about polarity. So I will see you in that video. Bye.